Let's put our knowledge of acid-base equilibrium and acid-base titrations to the test by calculating the pH of this titration at 4 different points: before we add any sodium hydroxide, after we've added some, at the equivalence point, and past the equivalence point. The first thing we need to do is to determine what equilibrium reaction we want to write to solve the problem that we have. So let's start with this first step before we've added any sodium hydroxide. So at that point in our beaker, we have added water and this weak acid called KHP. So we need to know something about this KHP and how it reacts with water, because that's what we have in our beaker. That's what we've added to our beaker. So let's just represent the KHP. It's our weak acid. Let's just represent it as HA. So we know that we have this weak acid plus water in our beaker, and that weak acid is going to dissociate into its conjugate base and H3O+. So we're going to need to know something about the initial concentration of this weak acid and the equilibrium constant Ka for the acid ionization of this weak acid. We can look up the Ka value and we'll find that it's equal to 3.9 times 10 to the minus 6. Now we need to know the concentration, the initial concentration of our weak acid. We know that we put 0.5 grams in 75 milliliters of water, and we know the molar mass of our KHP. From the mass that we used and the molar mass of the compound, we can get the number of moles of KHP that we put into our water. If we know the number of moles and we know the volume of water that we used, we can find the concentration, because concentration is equal to number of moles divided by the volume. The number of moles is going to be equal to the mass that I used divided by the molar mass. And so I'm going to have 0.5 grams divided by 204 grams per mole tells me that I have 0.00245 moles of KHP. And so if I know the number of moles of KHP, I can plug that into my calculation for the concentration, and I can calculate the concentration of my KHP, 0.00245 moles, and that's in a total volume of 0.075 liters, because 75 milliliters is 0.075 liters, and that will give me a concentration initially of 0.0326 molar. So now I know my initial concentration of weak acid, I know my equilibrium constant for the ionization of the weak acid, and so I should be able to calculate the concentration of H3O+. And if I know the concentration of H3O+, I can find the pH at this point before I've added any sodium hydroxide. So at this point, we're just going to do the equilibrium problem. So my initial concentration of the weak acid is 0.0326. I haven't put any conjugate base or any strong acid into my solution, and so to get to equilibrium I need to make X of the conjugate base and X of the H3O+, which means I need to use up X of the weak acid, and so I'm going to have 0.0326 minus X of the weak acid at equilibrium, and I'm going to have X of the conjugate base and X of the H3O+. Now, we can see that our equilibrium constant is small, and so we're not going to make very much product. Since x represents how many products, x is going to be quite small, and so we can ignore x relative to 0.0326, and so we can write that 3.9 times 10 to the minus 6 is equal to the product of the product concentrations, so that's just x squared, divided by the reactant concentration, which can be approximated as 0.0326 because I can ignore x relative to this initial concentration. And so I can solve for x in this equation, and I will find that x, which is equal to the H3O plus concentration, is equal to 3.56 times 10 to the minus 4 molar. And so my pH is the negative log of that. So if I take the negative log of that number, I get 3.45. And so my pH before I've added any sodium hydroxide is 3.45.